In the next series of lectures, we're going to be talking about Chapter 3 of the book, which discusses the kinematics and dynamics of a UAV. Now, when we say kinematics, we're talking about the relationship between our pose, which is defined as our position and orientation or attitude. So the relationship between the pose and our velocities. And then when we talk about dynamics, we're going to relate our velocities, that's going to be translational and rotational velocities, relate those velocities with our forces and moments. So let's go ahead. Oh, and so this video, we're going to just look at the kinematics, so the time derivative of our position and attitude. And then we're going to, in following lectures, we're going to look at the dynamics. So like I'd already mentioned, we're going to develop all that with respect to our Euler angles. So then in a following lecture, we'll talk about replacing our Euler angles with quaternion representation for our attitude. And then the final lecture in this series is going to be talking about numerical integration techniques. So all these lectures, we're building up this motion model, and the final one we'll finally figure out how to use it to simulate our aircraft forward. So forward in time. So let's go ahead and get started. As we jump in, we're going to look at, to start off, look at our aircraft state variables. So our aircraft state is going to be, as we describe it here, is 12 degrees of freedom. So it's a 12 state model. If we look at these real quick, we have the top three. Whoops. The top three, these are our position. So we have our position, and this position is defined in terms of the inertial frame. So the PN, PE, PD, that's our northeast and down position of the center of body of our aircraft. So the next three variables are our ground speed velocities, right? And we had previously called this V sub G in the body frame, but it's just our translational velocities. And these velocities are defined in terms of the body frame. So U is the ground speed velocity, just the velocity of our aircraft. Remember the wind triangle. Just the velocity of our aircraft measured along the along the IB, so pointed out the nose of the aircraft. V would be the ground velocity measured out the right wing of the aircraft, and W would be the ground speed velocity measured out of the belly of the aircraft. So there we have U, V, and W right there in that position, or in that figure. Okay, our next three variables are our attitude. Now the positions and velocities we defined in just one frame or another. Our attitude, if you recall, back from when we looked at each one of the different coordinate frames, we defined our attitude in a series of three different coordinate frames. So we defined our heading angle. Our yaw angle is defined in F super V, so our vehicle frame. And that took us to our vehicle 1 frame, which we defined our pitch angle, and our roll angle was defined based on the vehicle 2 frame. So we defined each one of the attitude angles, and we called these our Euler angles, right? And so in a future lecture, and these are an Euler representation, Euler angles, a future lecture will replace those with quaternions. But anyway, our Euler angles we defined in those three different frames. And then the final variables we defined, we're going to define in our body frame. So these are going to be the roll rate, the pitch rate, and the yaw rate. Now, we call them roll, pitch, and yaw rates, but we'll be careful, and we'll talk about it just a little bit here in a couple slides. These, we have to be careful because these are all defined in the body frame, right? Whereas our attitude was defined in 3 different frames. So we have to relate those frames to our body frame to talk about time derivatives. So P isn't directly just the time derivative. Well, P is. R isn't directly just the time derivative of our heading. Okay, so if we look at those velocities, these are going to be our rotational velocities. So our rotational velocities, these guys will be how our vehicle is rotating in our body frame. So P is going to be rotating about our IB axis, so we'll be doing rotations about that axis. So how fast are we rotating about that axis? Our Q is about the J axis, and our R is about the K axis, all in the body frame. So it's nice, all of our velocities, whether it be our translational velocities or rotational velocities, they're all defined in the body frame. So we'll pull this image back up several times. Now we want to relate all of this. We want to define a time derivative. So we're gonna call all of these variables. We'll call these our state variables. So here's our state. We'll get these variables. We'll have Pn, Pe, all the way down to P, Q, and R. All right, so we have all of these variables. So we're just pulling these guys, putting them up in a vector. We'll call that our state vector, the state of our aircraft. It defines where our aircraft is and how it's moving. What we want to know, we desire to know our time derivative, d dt of x. And we'll call this guy x dot. So what is the time derivative of our state? In other words, we could say this answers the question is how does it evolve over time? Okay. Now in controls classes, we talk about this generally in terms of a function. So we're going to say that as our simulation function, or often we'll call these our dynamics, so it's an abusive name just a little bit. So our motion equations, or I guess an abusive terminology. We'll write this as x dot is equal to a function of x and u. So in other words, we have a function of our state and our inputs. Okay, so we've already defined what our state is. What are our inputs? So over the next in this chapter, so chapter 3, we're going to say that our inputs are defined as just our forces and our moments. These are going to be our inputs. Now in chapter 4, it's not natural to say that our force is our input, right? We can define a force in the x direction or a force in the z direction. Not natural because we can't just choose what forces or what moments we apply. But right here we will use in this chapter, we will just use those inputs or the forces and the moments as our inputs. That's what we're deciding. Chapter 4 will then jump in and we'll say, how are these forces and moments produced by the actual inputs of the system? So where our actual inputs of the system is we get to define how our ailerons are moving, how our elevator's moving back here, our rudder, and how much thrust we're getting out of our propeller. So we'll get to that, but for this chapter, we'll just say that our inputs are our forces and moments. Okay, this is cool because then we can just see how the aircraft itself is going to be moving over time. And let's jump over. We can see this in simulation. So right here I have my aircraft. pulled up. I just have a simple control panel that I can reset it to the, oh, I got to go over the actual, I can reset it back to this state. And over here, I can decide what are going to be my forces and what will be my moments. And these are going to be defined in the body frame. So now, for example, if we want to apply a force, and we're going to do large magnitudes of forces because the scale of this sim, each block is 100 meters. And I've scaled up our UAV, multiplied it each dimension by 100 so that you could actually see it. And we'll, as we go through the course, especially when we get into path planning over larger distances, that's why we have that scale. But anyway, so that's why we have such a big force here. So we're going to apply 100 newtons in the X direction. And once I turn that on, you'll see that the aircraft starts to move in the north direction. So we have right here in the top left, we're plotting our north position variable, right? And it quickly goes off the screen. So we can reset that to see it again. So we reset it, right? And we just are quickly going faster and faster. And you notice that this is a quadratic in terms of its change, right? Because the force is going to affect the acceleration, which is 2 derivatives below the position. So that's pretty straightforward and intuitive, right? Let's turn off the forces. Here, I'll reset it so we can get back. Let's do it in the Y direction. So we can turn on a force of so much in the Y direction, right? And this is now very unnatural movement. We're just going to move to the side. And we see that the forces are going to affect, we get that same quadratic relationship to our east direction, so our position in the east direction. And we should have been looking at also how the forces affect our velocities. They affect our velocities in a linear fashion, which is really cool. So this second row right here is our velocities. So we have U, V, and W. And so they affect those in a linear fashion. And right now, the only reason that this is the exact time derivative is because the orientation of our aircraft, we see here we have 0, 0, 0. So our body axis aligns with our, the body axis aligns with the inertial axis. Okay, so let's bring those things back up. Reset our aircraft, come back, and then we can start. So the forces are pretty intuitive. This is just going to be a force in the forward. This is going out the right wing, and this will go down. So we could show that, and it's going to be the same. Now, I'm going to do a small value of this because you'll see why. I'm going to apply a torque about the x-axis. So again, remember the x-axis is parallel to this red line, and perhaps I should just show that frame, so our body frame instead of our northeast down frame. The only problem is then you don't see the aircraft as well. But so our torques are going to be applied about, we're going to apply a torque about the x-axis. And you would expect, as you would expect, it's going to start rotating about that x-axis. And so it's rotating about the x-axis, but now you'll see that we get some wobble in there. So even though we're applying it just about the x-axis, the physics tell us that it ends up starting to affect other axes as well. So we come back to our plots. We applied it about the x-axis, which is phi, and so we see that it goes up to 2 pi radians. That should be larger. Anyway, so we keep, for some reason that's, oh yeah, it goes up to pi, right? And then it goes down to negative pi. So this is just continually going forward and forward, more and more. And this starts to affect the other angles. So this is our phi, theta, and psi. So we see that we get some disturbance in our yaw. We get some disturbance in our pitch, although these ones aren't quite as large as just that phi. But we do have these cross terms that we'll end up seeing how those come into play. And similarly, let's turn off our our moments, and we'll reset our system. Okay. Similarly, we can come over here and we could apply a torque. Now let's change this to 0. 1. Okay, so we can apply that torque about the y-axis. So we see most of our movement is along the y-axis, but we start to see a little bit of wobble as well. So if we come in here, we do see a lot of torque now about the y, so we're pitching quite a bit, but we do start to see torque, or we do start to see effects in the other axes as well. And now this one was a bad one because it actually hits onto our singularity, right? In terms of when we pitch straight up, that's where our Euler angles are, we have a singularity. Okay, so perhaps let's stop that one and we'll do one instead in this around the z. And we won't hit that singularity. Okay, so we'll reset it, and oops, I got to publish it. And now we'll start to see it rotate about the z-axis. And again, you start to see some wobble there in that frame, right? So we are applying torque on the z body frame, the z-axis of the body, and it causes disturbances in other values as well. So now we've got that torque that's causing our this rate to increase linearly. And we see that in this angle, and we see these small perturbations on our pitch and our psi. Okay, excellent. So we inadvertently saw our singularity. But we do see how our forces are nice and straightforward. Our translational motion is really great. And we get that rotational motion starts to cause some strange behavior. It starts to cause some wobble in our system. Okay, so let's go back to the writing. Oops, there we go. Okay. So let's come in and in this lecture, we're actually not going to jump right into the forces and moments, but let's start doing that, getting that time derivative, so we can start to figure out how things are related. So the very first thing we're going to do is look at the translational kinematics. So basically, when we talk about translation, all we're talking about is our position. So we're going to say, how does our position vary over time? Well, if we're going to take the time derivative of our position, p dot, our position of Pn, Pe, and Pd dot, we'll just get that's our velocity vector in the vehicle frame. Now remember, the inertial frame and the vehicle frame, we can define vectors in either one, and they're equivalent, right? So this would be equal to our v in the inertial frame, because those two set of axes are parallel. Now, we're saying that our states, we have our states defined as u, v, w, and those are in the body frame. So to get our velocity vector in the body frame, all we do is we multiply that by our transform that'll take us from the body frame to the vehicle frame. All right, so we take our UVW right here, multiply it by that transform, and we had previously defined the rotation matrix from the vehicle to the body frame, but again, all we have to do is take the transpose, and voila, we take that that matrix that we've defined in previous lectures, multiply it by UVW, and now we know how our position is varying with time given our velocity. So we know how the position varies with time given the velocity. Okay, so that's great. So we already have 3 time derivatives out of the 12. So that was pretty quick. Rotational kinematics. Rotations always make things slightly more difficult, right? But we defined, recall we define our time derivatives in one frame. We defined our states. Sorry, let's go back up here. So now we're trying to relate our position with our rotational attitude with our rotational velocities. So our rotational velocities are defined in the body frame, and our attitude is defined in vehicle 2, 1, and the vehicle frame. Now, right here, if we look at phi dot, we say that it's defined in the body frame. Now, the reason that phi dot is defined in the body frame, where phi, we said, is in the defined in the vehicle 2 frame. So that gets a little confusing, right? Because we say that phi dot is in the body frame. Well, if you recall, the vehicle 2 and the body, these guys share the z-axis. So they have the same exact z-axis. And so if we're talking about perturbations about that z-axis, we could talk about those in either the body or the vehicle 2 frame. Now, phi is absolutely in the vehicle 2 frame, but its time derivative, how much it's changing, we can talk, it's going to be equivalent whether it's in the body or the vehicle 2 frame. So phi is still nice. If we look at theta, right? So immediately I say phi is nice because it's immediately in the body frame, or the time derivative is in the body frame. Man, I've talked that one through really well. Now, theta dot, similarly, and let me make this share the z-axis. Theta was defined in the vehicle 1 frame, but it shares the y-axis with the vehicle 2 frame, right? So it shares the y-axis. So all we have to do to get from the time derivative of theta to the body frame, which is where we're going to relate it to P, Q, and R, is we just have to rotate from the vehicle 2 frame to the body frame. So even though theta is defined in vehicle 1, its time derivative is going to be defined equivalently in either vehicle 1 or vehicle 2 frame. So we have to have this rotation matrix, which is a function of phi. Okay, now psi, right, similarly, it's defined in the vehicle frame, but it shares an axis, the z. Oh, back here I'd said z. That was x, right? Sorry. Shares the z-axis with the they share the z-axis. So we can talk about the time derivative in either the frame 1 or v1 or v. So if we get psi dot, then all we have to do is multiply that time derivative by the rotation matrix, and again, this is just r from v1 to our body frame, right? We're just chaining those together. Okay, excellent. So now we we just put these things all together. So obviously that's just the same as there. Here's our rotation matrix. That guy goes there. Now this rotation matrix is defined there. That one's defined there. And we have our final, our psi dot, right? So we do some algebra and we're left over with this matrix, which almost looks like it could be like a rotation matrix, except for it has a non-zero component there. So it's not a rotation matrix at all. But the great thing about this matrix is, and you can kind of tell that from the diagonal, but it is invertible. So what we do is we invert that to get the relationship, because what we want to do is define the time derivative of our attitude. So over here is the attitude ddt of the attitude, right? In terms of our rotational velocities. So again, these were our rotational velocities. Now, I said that this is invertible. That's almost true, right? The one thing you're going to note here is that we end up getting a secant, right? We have 1 over the cosine of theta, which is problematic, right? So again, this goes back to when we pitch all the way up, like we just saw in our in the sim. When we go all the way up, then we have these discontinuities in what our Euler angles are going to be. And so we do have this singularity if theta is equal to plus or minus pi halves. Okay. So as long as theta is not plus or minus pi halves, then we don't have this singularity, and we're good to go. We see it here as well, right? Excellent. So we can invert it, and now given, so here, given P, Q, and R, we know how our attitude varies with time. Okay, this is fantastic. So we have done our translational velocities, that we know how position varies with time. Now we know how our attitude varies with time, and we can we've gotten 6 out of the 12 equations. All right, so we have 6 out of the 12 time derivatives are already defined. We have these matrices, which are largely are a function of our attitude, right? Where we're relating our translational velocities and our rotational velocities to the pose states. So the remaining 6 equations we're going to get when we apply Newton's second law to these translational and rotational motions. We're going to use Newton's law, and we'll relate the forces and the moments to our translational and rotational velocities.